definitely changes your life. It helps you establish relationships that are really tighter because you already have a lot of things in common in the way you think, work, want to change the world around you.
As you get involved in IEEE, you really get a sense that you want to give back and to grow the community that you have.
I think there's a natural intersection between IEEE and its role in promoting the emergence of new technologies and entrepreneurship.
IEEE was a great channel to get to connect with professionals in the field. You never know what's going to happen when you meet so prominent people that are foreseeing the future.
What has IEEE brought me? I've worked full-time in power system automation, which we call smart grid, for over 41 years now, full-time. And the job changes I've made were through industry friends that knew of opportunities that I wouldn't have known otherwise and opened up the door for me. And many of these industry friends I met through IEEE.
What other place can you try to take a risk of doing our presentation skills and bringing in somebody from industry to talk to other scientists and engineers? I've been a member of IEEE for 25 years, and I still talk and mentor about this to this day.
IEEE has given me opportunities to network in terms of getting to know the leaders in the field, and also has provided an outlet for those leaders to know what I'm doing. So it's been good for both of us.
Given the world that we're living in now, where everything is pretty much about the internet and about connectivity, it's actually a good time to be an engineer and to be a telecommunication and networking engineer.
We know it's about the dynamics between people and people groups where our future is. And engineers can facilitate that, but they don't have the answers. It's the answering of us together as a community, not as engineers alone. So engineering is not going to solve the world, but it's going to facilitate that problem solving and getting together.
At IEEE, we believe technologists are the key drivers of tomorrow's innovations because we can really do what IEEE's motto states. We can advance technology for the benefit of humanity.
I always wanted my education to mean something more than just, doing a day job that pays my checks. I wanted to see how my background in engineering and other things could have an impact that can make somebody's life better.
Being able to connect our members with younger students and engaging them to emphasize that it is important, that what they are pursuing in their STEM careers is truly going to be the next thing that affects all of humanity, because all technology that we make is affecting people, and it's not just IEEE members, it's everybody.
Hello everyone, thank you for being here, attending this talk, and thank you for you, Professor Mason, for accepting our invitation for this talk for the B branch, for this special edition 2021, in virtual edition, I could say. I will begin with a short biography about Professor Andrew J. Mason. He received the Bachelor of Science degree in physics with highest distinction from Western Kentucky University in 1991, the Bachelor of Science in Electrical Engineering degree from the Georgia Institute of Technology in 1992, and the Master of Science and PhD degrees in Electrical Engineering from the University of Michigan in 1994 and 2000, respectively. From 1999 to 2001, he was an assistant professor at the University of Kentucky. In 2001, he joined the Department of Electrical and Computer Engineering at the Michigan State University, where he is currently a professor. His current research interest includes mixed signal circuits, microfabricated structures, and machine learning algorithm for integrated microsystems in biomedical environmental monitoring, sustainable lifestyle application, the design of augmented human awareness system, wearables, biochemicals and neural sensors, and lab-on CMS integration of sensing instrumentation. Thank you for being here for talking about your talk about augmented perception and new generation wearables and human-machine interface. The floor is yours.
Well, thank you very much, Martin, for the invitation. I'm glad everybody is able to take some time to look at this talk. Let me share the screen. And there we go. Okay, excellent. So the topic today is augmented perception. And but before I jump into that, I like to give a sense of who I am and where I am. Michigan State University is in the middle of the southern side of the state of Michigan. We're surrounded by the Great Lakes. So up here, where the star is in the overall map of the United States. So it's wonderful to be meeting some new people virtually in France this afternoon. And again, thank you for your attention. I'm going to start by just kind of getting everybody to think about the general concept of augmented perception and bringing us all into a similar definition. So augmented, and particularly now we're referring to human augmentation, just means the use of tools to achieve more than humans could do with just their natural body. So if we ask ourselves, what's an example of a tool or technology for human augmentation? A typical response that people come up with is a mobile phone, which is quite true. It has clearly augmented the way we interact with the world, and it provides us a lot of additional capability that's outside of the natural human capacity. So in engineering terms, all these augmentations can be put into examples of either inputs, sensing capabilities, or outputs, actuation capabilities. Now, the other term here in augmented perception is, of course, perception, which by definition is the ability of humans to become aware of something. And then from a psychology point of view, it's worth pointing out that, again, psychologists will separate the concept of perception, which is the observing of something, and awareness, which is the consciousness of it. So we can perceive something, but then we have to integrate it into our cognitive processes, then we become aware of it. So I have recently changed the thrust of my research and now lead what's called the Human Augmentation Technologies, or HAT Lab. And how we got started was by asking some very simple, basic questions. What does it mean to know something? And what is it that we know? Knowledge is the information available without any effort that we can act on immediately. And what is the true or technological limitation of us knowing more? My devices, my mobile phone knows things that I don't. And why don't I know that? So what are the bottlenecks to us getting that knowledge from machines? Of course, we all know some basic facts, right? We have a lot of knowledge packed into our brain. We know when we were born and what color the sky is. And we have some information about our immediate environments. There's light on in this room. I know it's daytime outside. These are the types of things that we know without any effort. So this represents awareness. However, there are a lot of things beyond those things that we do know that we would like to know but don't. So if we think about some things that we don't know, if we were attending this lecture in a normal format where we were all in an auditorium, we wouldn't know how many people are sitting behind us. We always have some sense of what time it is, but precisely the time we need to look at a watch or our phones to tell us this. Outdoor temperature, all these things. There's a lot of information that we're constantly asking ourselves that we have to look to a machine to provide that information. And that even extends to knowledge about other people. If I were sitting in a meeting room, would I understand if the person next to me was happy or sad today or sleepy? This is information that, interestingly, we know that our technological devices can determine some of these things, particularly in this growth of wearable devices. These devices can sense these things that we don't know, but then what is the bottleneck in us knowing them? Why can't we make that part of our everyday knowledge? So can we do anything to enable humans to know more about the things that machines know in real time? And that's really the question that drives my research right now. We call this this moment sort of the AHA, or the concept of augmented human awareness is AHA. So in English, this term AHA, A-A-H, is an exclamation that expresses the discovery of new understanding. So it seemed very fitting that we have our AHA moment in our research lab, where we wonder, what is the limit of technology to make superhuman perception? And that technology would allow us to know more. And this has led us to all of our work under the concept of AHA. So technology for superhuman perception and greater knowledge, greater knowing. So how does human augmentation work? Well, it all starts with the human, of course. And if we envision that, that everything that a human could know is represented by this globe here, and that everything that humans know about the everything has to come into our brain through our senses. Right? It's the only pathway into our brain. So everything we know gets interpreted through our eyes or hands and ears, and ultimately becomes part of our cognitive processes. So whatever our natural senses allow us to see, that's the portion of everything that could be known that we have access to. Well, interestingly, we keep building machines that have better and better access to information. And sometimes this information overlaps with what humans can sense, but often it's things that we can't sense. And that's what motivates us as engineers often to build new devices, is the ability to sense something or detect something that humans can't naturally do. So humans have this information, or excuse me, machines have this additional information. And my research is really all focused on how can we get this built into the everyday operating lives of humans. So one element of that is to take these machine capabilities and then bring them into a wearable real-time environment, something that I can be portable, I can carry around with me, that can do that sort of detection, and then finding ways to transfer that information, get that into my cognitive process. Well, this leads us to the observation that any external inputs, whether it's coming from the environment or a machine, has to pass through the human sensory network. I mean, our brain is locked inside this shell, I'm sure quite by intent, and there's no other way to get into it except the invasive surgical methods, except through the human senses. So everything we know about other humans, about the environment, or anything that machines could tell us, all have to come through. So any solution will end up co-opting human sensory networks. For example, your mobile phone co-opts your eyes and ears. You have to look at it to read a text message or listen to it for a notification. So the only way that mobile phone is getting into your cognitive process is through your human senses. If we can work through and improve this human machine feedback pathway, then we can augment our perception to go greater than natural human sensing. And that's the concept of human augmentation. So to give you an example of this, I want to show you a short video where it's in our lab. We have taken a human, a student, and set them up with sensory deprivation. So they have a mask on so they can't see, and they have feedback headphones on so they can't hear anything. But we've equipped them with electronic sensors that they're wearing on their chest. And then we've given them a different form of feedback from those sensors through a tactile stimulation wristband. It's a vibration wristband. And so everything the sensors get, they send to the person through the tactile mode. And we show that the person has understanding of audio and visual information, even though they don't have access to their audio and visual sensing. So just an example of how this would work in the case of natural human senses not being performing normally. So let me transition here. Okay, so in this environment, this is a student who's wearing the badge, and we've defined the information we're going to be looking at in 3 states. He either hears someone talking, he knows someone is near him, or he knows the lights are on or off. So now when the lights go off, notice that he detects that, or the sensors detect that, even though he can't see it. And this information is transferred through vibration to him, and allows him to make a decision to hold up a flashlight, indicating that he knows that the lights are off. Now, when another student approaches him, the sensors detect that, and he holds up his hand to indicate he knows someone's coming toward him.
I'm talking, so...
And now when someone's talking, he waves the flag to say that he knows that someone's talking. And now we change the environment again, and he's able to detect it. He knows when the lights are turned back on and off. All right, and all this without any of his own sensing. Okay, so that was just an example. And what it leads to is the concepts of what we're trying to do in our research right now. And there are 2 main goals. And the first one is we want to look into how can sensing be done in real time with wearables, and what are the bottlenecks. In particular, I'm interested in my lab in how we can create superhuman perception of social interactions. So if there's a machine, which could be a wearable device, that is able to detect parameters of social interaction, how can we improve those capabilities? So this is sort of the real-time sensing side of what we do, but we also work on the feedback or communication pathway from the machine to human. And our second thrust, how do we communicate machine-sensed information to humans? Particularly, how do we do it in an unobtrusive and discreet manner so nobody knows around us when we're getting in new information? We aren't disturbing other people by notifications or alarms or anything like that. And we want to make sure that we are avoiding the congested audio and visual sensory channels. I want to create technology that will allow me to engage in my life the way I normally would, but still have other information, have augmented understanding. So we've commented before that getting information into the brain is quite a challenge. And in my lab particularly, we're looking at tactile communications like I showed in that video, particularly electro-tactile, which I'll discuss a little later. So is there a way that touch can be used for communication? So I often will ask an audience, if you had machine-augmented superhuman perception, what was some things you would like to know? And often the answers come back related to things about other humans. You know, is this person I'm talking with happy or sad? In my world as a professor, I often am wondering, are my students engaged and listening? Are they paying attention? What can I do to engage them better? It's the idea is getting information that helps us to perform our task even better is among the top goals. So what do we have to do next in order to improve everything in this area? We noticed that in terms of behavior monitoring and social interaction monitoring, that our self-awareness is really quite flawed, and varies a lot among humans. So the ability of a neutral machine to come in and make assessments of social interactions and provide that information to all the people could be quite a boost to our social interactions, including work productivity and things like that. So we are asking the research question of, can machine augmentation improve social interactions? Also in this COVID environment, when many of us have been on lockdown and have switched to virtual forms of communication, as this presentation is right now. We've started to look at how the virtual environments, how we can improve those virtual environments. And particularly the idea virtual means that I'm not physically with other people. So social interactions are entirely different. Can we use machine intelligence to improve virtual interactions? And then lastly, on the communication feedback pathway, machines to humans, what can we do in terms of tactile communication? Can we create unobtrusive and discrete pathways for communicating? And particularly, we're interested in electro-tactile. So these are the three topics I'm going to dig into a little more deeply. And first, in the concept of behavioral monitoring. This requires, as an engineer, we know that monitoring social interactions requires us to make a deep dive into psychology, things that engineers aren't typically as aware of. In order to understand the structure in which we would like to engineer a solution. We do know that the quality and quantity of social interactions has a major impact on humans, on our physical health and our mental health. The decrease in the quality of social interactions has an associated increase in depression and even cardiovascular disease. So improving those social interactions can be very valuable for our welfare. However, social interactions are highly complex, and I'm not going to get into the details of this model we've developed, but just to point out that we have, for individuals interacting, individuals have all of their own personal factors. The environment plays a role, and whether we're out at a sports match together enjoying this, or in a classroom environment, or the environment changes the social interactions a lot. And then the dynamics of the individuals interacting. So there's a lot of different dimensions that have to be brought into this. And again, I'm going to kind of ease through some of this. But from a personal level, it goes from everything from our very short-term emotions, which could be based on whether we had a bad experience walking to work this morning, to all the way up to our long-term personality traits, which are established throughout our lifetime. So there's a lot of temporal modalities within our personal factors. And then one of the things you note is that it's important to remember that a human species was communicating and interacting, socially interacting, long before they developed language. So we have integrated into our evolution nonverbal communication channels. And being able to tap into those is going to be one of the key elements in getting machines to monitor social interactions. It's also valuable to note, I said earlier that humans are really poor judges of themselves, and us self-monitoring social interactions can be very limiting. It's also true that people tend to not be aware of their own negative biases. So we call this an unconscious behaviors that can affect our social behaviors. For example, something that's called implicit biases, and especially in the workplace. These are things that people are really bad at self-judging. So they involve a combination of things, from the individual human emotion to what our intentions are and how we're performing communication. All of those things go to build up our awareness of these behaviors. And we really need a solution that will allow us to increase our situational awareness, allow us to gain some understanding of our implicit biases so that we can correct them and perform better during our social interactions or workplace interactions. So we're looking at technologies that will allow that, and to asking the question from a research point of view, can machine augmentation improve our social interactions? So as an example of the kinds of platforms we're looking at, imagine that we represent a social interaction in a work environment by these 4 people having a meeting, let's say. Can we develop technology that will monitor their behaviors? And then from that behavior, from that data set of monitoring sensor data, we have to be able to extract behavioral features. And once we can do that, then we can apply it in some sort of feedback that will represent quantities that will allow the individuals to then make decisions with more information, more informed decisions. So we call this the situational awareness. So as an example of the types of things we'd be looking at, I've shown this visually. Now, the idea, of course, is not to present this visually to the people, but in order for us to discuss it here, it's presented visually. So quantities like a conversation density map. So with this blue diamond here would move around closer to the people who talk the most. So here we see orange and gray are the ones that are dominating the conversation. So the conversation density is over close to them. If we had an awareness of this during our conversation, we would better be able to decide, should I speak now? Should I let other people speak? Should I encourage someone who hasn't spoken much to get involved in this conversation? We can also measure the dyadic or two-person attentions. How much are two people looking at each other? How much does one person nod their head when the other person speaks? This sort of mutual attention can be measured, and we could indicate it. It's indicated here as like the thickness of this pink line. And then finally, emotional arousal. This is very individual, but it can be key. If someone says something that frustrates you or excites you, our ability to monitor that in real time and let people know, have a sense of where people's emotional arousal is during the conversation can be quite beneficial. So these are the types of information that we're trying to sense and then process through algorithms in order to come up with better situational awareness. So to start this, we ask ourselves, what do people look for when they are involved in these interactions? So if you were in an interaction and you wanted to get a sense of how much someone was paying attention to you, like I often do this as a professor when I'm in my classroom, looking at the audience and trying to decide how much attention, or do I need to stop and wake everybody up or change my modes in order to grab people's attentions. And what do we rely on in order to get this information? Well, visual contact, right? Are people looking at me? We also rely on verbal feedback, people answering yes or uh-huhs, these types of, these are still considered, these utterances are nonverbal, even though they're, so these are the types of channels that we would normally look for. If I wanted to get a sense of someone's emotional state, I would listen to the intonations and whether I could tell if there was happiness or sadness in their voice whenever they talked, or facial expressions, frowns and smiles. To determine who's leading a group is another thing we might look at. So we can say who's talking the most or talking with the most authority. So all of these things, if a machine were to capture these social elements, we note that a lot of them can be managed by having microphones and cameras. Through microphones and cameras, we can answer most of these questions. So in my lab, we're looking at not only taking microphones and cameras, but also adding in physiological sensors and the monitoring of movements, physical movements, in order to create the psychophysical awareness. So these will be a combination of the physiological processes, things like your heart rate, for example. If your heart rate changes, or a change in the variability of your heart rate is an indicator of arousal. Also through the microphone, we can and the movement sensors, we can get a lot of nonverbal messaging. Then all that sensor data will be applied to algorithms whose job is to extract ultimately what are the human behaviors at play at any given time. And this has to be able to account for personal factors like your emotion and your personality, and also has to be able to look at aspects of social behaviors, collaborations, group performance, these things. So the combinations of the right sensors and the right algorithms will ultimately lead to better technologies for augmenting human awareness. If you look at what's been done, we've seen for the past decade or so, people have been building microphones into wearable devices and other things like this in order to monitor groups. We also see that there's been some early work in emotion monitoring using things like inertial motion and this kind of glove that combines lots of sensors, EEG monitors for brain waves, and EDA for electrodermal activity, looks at skin conductance, EMG looking at different muscle movements. So a lot of these wearables have been developed, particularly in the past 4 or 5 years. It's been a really hot area. And with the social behavior monitoring of the past, it's all been focused on group level work. Is the group interacting efficiently? These emotion monitors have all been done on individuals, looking at just an individual's emotional state. And one of our goals is to try to merge these things so that we get the interaction of individual information within a group environment and overall to improve social interactions. However, there are many technical challenges that have to be overcome in order to make this real-time and wearable. So some of those include at the pre-processing and extraction of the signal features, there are all the different sensors you need have different time alignments. So getting all that data like time aligned is a critical challenge, and many different sensors output features or raw data with different formats. That becomes a real nightmare. And then there's a lot of noise introduced in these sensors. So we have to do sensor fusion or different sensor calibration techniques in order to, for example, extract, if someone's moving their hands around, we don't want that to change our assessment of their physiological sensing, but a lot of times those sensors are subject to that kind of noise. So this movement artifact removal for physiological sensors is very important too. There's also sort of two paradigms of processing methods. One is where you focus on the individual, so a subject-dependent models. They tend to be very accurate, but it requires me to get a lot of data for all individuals, which is nearly impossible. So we could have subject-independent models that decreases my data burden for training my algorithms, but ends up with something less accurate. So how can we come to some compromise in between these elements in order to make the best and most accessible processing methods? And then we have to pay really important attention to our training data set quality. So if we do things in the lab, we don't get natural responses. To try to do something in a natural environment has many challenges. Making sure our algorithms, our training data sets don't have any bias themselves is important to eliminate bias from the algorithm. All these elements have to be taken consideration in how the training is done, how our data gets collected. So these are the key challenges that we faced in the area of creating new algorithms or creating new social monitoring capabilities. For the second area, I want to talk about behavioral monitoring and distance collaboration or virtual collaboration. So clearly, our world has changed over the past 2 years, and there's more and more virtual communications. Everybody's working remotely, and a lot of our meetings and interactions have become virtual. So the challenge of virtual meetings, while there are, of course, many benefits, is that we have a much reduced level of personal engagement. And this affects the level of rapport. Rapport is that sense of connectedness we feel to other people that we're working on. That's very difficult to do in a virtual environment. There are, of course, benefits such as we get to practice our social distancing. It stops the spread of the virus, and we're protecting the environment. And we're going to probably continue this into the future. We're going to see more and more of this because the idea of eliminating driving and reducing pollution is very promising. A lot of indicators that work efficiency is improved and worker happiness is improved by some level of virtual work. So if virtual interactions and virtual meetings are here to stay, what can we do to make them better? There are some real limitations, though, in virtual environments that some of the modalities I talked about earlier can't really be employed. For example, it's hard for me to emerge in physiological sensors in virtual monitoring because those might not be there. In a lab, yes, but in everybody's home, not so easy. So all of these type sensors that we showed earlier, maybe we can come up with some methods in the future to make them more ubiquitous, to make them more common in everybody's home environment. But what can we do that is readily available now? Well, inherently, we have sensor or cameras and microphones in our virtual environments. It's a necessary part of virtual meetings. So they're great sensor sources. What can we do with them? We also have high computational power. We're not limited by what might be on a wearable device because you've got your computer or your laptop there that can do the processing. So we're really trying to dig deep into what level of behavior monitoring can be achieved by cameras. For example, we know that there are technologies for doing eye gaze, eye tracking, facial expression monitoring. We can also do with the camera body movements, orientations, and postures, possibly even physiological parameters, including your breathing rates and heart rates. However, all the work on that's been done with super high resolution cameras, not typical of the webcams and laptop built-in cameras. So there are some things that are pretty we're ready to, technology's ready for, and some things that really need some work. So we started this off by just looking at this open source tool called OpenFace that is there for video analysis. It detects your head pose and orientation, and then it tries to make some interpretation of nonverbal communication channels, including nodding, the orientation of your head, and gestures that you might do, including like shrugs or even tilting your head maybe is a form of a question. These types of things, it tries to give you the information where you can extract that. The gaze is very important for us in tracking attention because it allows us to see who's looking at the speaker at any given time or who's wandering around. In virtual meetings, we found a lot of people end up staring at the backgrounds of other people or looking at the bookshelves and things, and then they get disconnected from the meeting. So if we can tell who's gazing where, we might be able to provide some feedback that would help everybody in that meeting be more productive. So OpenFace also produces something called action units. So these are fundamental actions of individual muscles or groups of muscles in the face, and the combinations of those can be used to predict certain types of nonverbal communication, which I'll show next here. So these action potentials can be combined to represent things like happiness, sadness, surprise, and there's a whole list of them here, which is just, this table shows which different action units, when combined, tend to represent certain things. And we can train these data to be more accurate also. So here's the way this kind of concept works. From the video, we can extract data about awareness, including your affect, mood, attention, and engagement. And let's see. All of these show great potential for being extracted from a camera. So I have a little video sequence here. We'll play this, and you can see as the participant smiles or frowns. And then you can see the program's able to track their head motion and their eye gaze as they're looking around. All right, so that's just the open source system that is a great spot for anybody interested in this can grab this and start working on it. There are certainly still a number of challenges that need to be overcome. In fact, we have been doing a lot of work to determine what social cues that we would like to be able to monitor during virtual meetings. And that work is ongoing. So there is some other work that's being done in addition to just eye gaze using cameras that is important to notice also. So for example, heart rate and respiratory rate have been done using video analysis in the work shown here. And there's been work using even cell phone cameras mobile phone cameras in order to find respiration rates, and even using heart rates for PPG monitoring using a camera. So there are a lot of physiological things that can be done with cameras also, and this is ongoing work that can continue to be integrated. Although there's some great work out there, we still need to make a lot more progress in being able to understand and detect the emotions and behaviors of individuals using camera type framework. Oh, sorry. I meant to say that what's been out there has all been focused on individuals, and what we're really interested in looking at now is how we can look at the dynamics of interactions of groups utilizing all this individual information. All right, now turns to my third and last topic of machine-to-human feedback, or finding new pathways into the brain. So as we said earlier in the talk, getting information into the brain is quite challenging. And there are only two ways that we can do this, largely through non-invasive methods, which allow us to co-opt existing sensory pathways. So printing information on my mobile phone, or putting text on a screen, making audio notifications, or even vibration notifications are ways that we can non-invasively co-opt existing sensor channels. And of course, then there are invasive methods, nerve cuffs and brain implants, which can be considered, but are usually only even options if there's some sort of surgery needed because of other reasons. So we're really focused on non-invasive methods that everyone could apply. It's important also to think, when you think of, we got to look at how cognition occurs and see what some of the issues are in order to find technologies that can overcome those challenges. So all the information that comes through the human senses ultimately gets, so we represented in this diagram down here as sort of a multiplexing process. So all the information is coming in, and the brain has to decide what to give its attention to, and then only that information can become part of our cognitive process. So the process of allocating brain resources to a task is the definition of attention, and deciding what to ignore. And that becomes really important when you're talking about adding other information in. You want to augment the information coming in. You have to understand that the brain already has a filter that's going to be cutting down on things. So you have to work with that in a friendly way. So finally, once attention gets to work and decides what it's going to pass on, only then can the information be processed and then used to store in a memory. So it's important to keep attention in mind when thinking of how we're going to communicate new information to the human. So here's an example. Imagine that we wanted to make a simple observation. Is this light, is this LED on or off? So if we were observing this with our eye, then this light has to come into our brain at the visual data rate of about 10 megabits per second. So, however, it's just a single binary event. At any given time, it's a 1 or 0, it's on or off. Yet, the way for me to use my eyes, I have to grab way too much data in order to make that decision. So it represents a good example of where we might be able to bring a machine in. So if we use a machine, it can help us observe that light with a lot less attention, because it can take that information, distill it down to this single bit, it's on or off. And so we ask ourselves the question, if the machine can get it down to a single bit, but my human eyes need a lot more bandwidth, it does not make sense for us to, rather than get that information to the human through their eyes, get it through a machine that is able to encode that into fewer bits. So that's an example of the things we want to take a look at. It is true, however, that audio and visual feedback are the easiest and the most common. We all rely on these methods every day. I'm staring at a screen right now that's giving me awareness of what's going on through my eyes. However, that's a great data load on our brain. Like I said, about 10 megabits per second. If you're trying to get in a multitasking environment where we have multiple things we're trying to watch and hear and all the sensory inputs coming in, we really overload our visual and audio inputs. We overload our attention. So it's really beneficial for us to explore new pathways of getting information into the brain. And we're going to show you how, because audio and visual channels suffer these problems, they tend to be obtrusive and distracting, and they have limits in our attention span, that there's another signal channel that remains open for investigation. And that is the non-invasive pathways into the brain through tactile stimulation. Particularly in my work, we're interested in looking at electro-tactile stimulation, shown here in this prototype model where we have an array of electrodes on the skin, and we can play a certain waveform in, and we can learn to interpret that as a specific signal. So let's take a look at, first here's some of the ideas of tactile communication is certainly not new. In fact, Braille language has been out there for a long time as a way to do visual reading, but through tactile inputs. And so we know that the nerve endings in the skin can be used for unobtrusive communication to the user. They don't occupy our human sensory inputs of sight and hearing. And we have a lot of tactile receptors. In fact, the human skin is the largest sensory organ in the human body, and it remains largely underutilized by humans. We don't ask ourselves what our skin is feeling very often. So there are some examples of work that's been done, shown here, using what's called a haptic belt, vibrations going through a belt, and even tactile stimulations on the tongue and tactile stimulations on fingertips. There's a lot of work being done for haptic gloves so that a person can feel what a robot feels. What we're interested in doing, though, is not applying the sense of touch back to you so that you can repeat the sense of touch, but rather putting data streams in through our tactile channels. Within tactile communication, there's basically three modalities. There's vibrational, which you're all familiar with probably when your mobile phone vibrates. Mechanical touch, which is just what you would see when you touch your own skin or anything causes pressure. And then there's electrotactile. So electrotactile actually communicates, it changes ion flow through the subdermal area and can excite nerve bundles. We can also have intrusive methods where we do a similar thing. We put cuff electrodes, or different types of electrodes can be put into the nerve channels in order to excite the individual neurons. So, but electrotactile is unobtrusive and it achieves very similar things, just transmitting through the skin. All right, so there's a little more detail probably than we need here on about the skin, maybe more than you'd want to get into, but this is discussing electrotactile and how it works. Basically, you put two electrodes, sort of an emitter and a collector, and then this ionic current passes through the dermis, and then this, if you put the right waveform on it, it will initiate action potentials within this nerve bundle. So in your brain, it feels like something that is touch-based. So we're hijacking that nerve bundle. We're not exciting receptors. So it's new information coming into the brain. And I can tell you, as being a subject of this experiment for quite some time, that you quickly adapt to it, but it's a really unique sensation because it's just something we don't normally get. It's not like a shock, and it's not like you're activating muscles at all. It just feels more like an insect crawling on your skin or something like that, or the wind blowing on your skin. And but we can modulate lots of different waveforms and come up with almost a vocabulary of things that can be transmitted through this tactile method. I'll skip the rest of the biology on this and just move on. So I'll summarize here with the future challenges and directions. In terms of sensing modalities, there's certainly a lot of work to be done in health and physiological sensors, and work in environmental safety, human behavior, social interaction monitoring. and sensing through virtual communication channels. All of these have a substantial amount of work that can be done. There's also a big body of work that can be done in terms of signal processing. So I would say that to some degree, the sensors are more advanced than the algorithms at this point in time. So a lot of the upcoming work needs to be put into the algorithms. And machine learning has given us a lot of tools, and we need to apply these back to this sort of augmented human types of environments. And sensor fusion and decision making. The other aspect of this is it always needs to be continuous or real time. If I know tomorrow about something that's happening today, it's not going to help me solve that problem today. We also need these things to ultimately be built into our wearable devices, so concepts of edge computing. And ultimately, we're trying to merge sort of psychology and neuro engineering all together. And then this idea of human-machine communication really needs some new thought. We need a new way to communicate with high bandwidth in order to get more data in to increase our situational awareness. Well, that wraps up my talk. I'd like to thank the IEEE chapter for inviting me in to do this presentation, and particularly thank my students, Silmarie, Asan, and Sina, who led each of those 3 thrusts that I discussed with you today. And thank you.
Thank you very much for this presentation. It was really clear and very interesting. And if you want, we can skip to the question.
Yes, I'm ready for any questions that might be there.
Do you want me to read the question?
I don't see any yet.
Okay, no, I will try to read it then. Oh, do you see it?
I see this.
Okay.
I'm trying to think of the right way to answer that. I read the question. It's no, it's definitely an uncharted area, and that's what makes it exciting for researchers. We don't know the answer to this. We don't know how the brain's going to respond to a lot of additional information coming in channels that we're not used to using. It will have to be determined experimentally how much capacity our brain has for that. We know that additional visual or audio information, that there's a bandwidth limit, right? There's only so much we can take in. But what we're really interested to explore is how much additional information, say through tactile inputs, will our brains be able to manage? No one knows that because no one's yet built a machine that allows us to challenge that. And that's what we're in the process of doing. Actually, we should pretty soon have something ready, and we'll start testing the ability of people to learn these tactile inputs, and then their ability to integrate them in with other tasks. So while they're performing maybe manual labor tasks or cognitive tasks, but they're receiving additional input through a tactile means. So it remains to be seen whether it will be an overload, or whether it probably, I would say it's very likely that initially it will be an overload. So the question is really not, is it an overload, but is it an overload that we can adapt to? Can the brain adapt to taking this extra information and building it into effective cognitive processes? That's a great question, though. Thank you.
I will show you the next question.
Powering is not something that I have put a lot of effort into. I am traditionally a CMOS integrated circuits guy, and so we know that everything that we're doing here, including electrotactile stimulation, can all be done using modern ICs. So I don't envision powering to be a problem. There are certainly some possibilities of techniques, for example, brain monitoring. I think that anything we can do to non-invasively monitor neural signals, particularly brain neural signals, will be highly valuable. in any of our future human augmentation systems. Some of those right now would be pretty powerful. For example, using ultrasound techniques or something like that might require a lot of power. But your basic physiological monitors have gotten very power efficient, and I don't see any challenge in doing most of these things. The algorithms, on the other hand, that can be difficult. We don't want to create an algorithm that requires a supercomputer to generate its results in real time. So the edge computing concepts, things that allow algorithms to be implemented effectively, but with very low resource usage into, say, microcontrollers, there's still a lot of opportunity for work in that area.
Thank you very much. I have myself a question. Can these new technologies one day allow human beings to recover lost senses? I talk about non-invasive technologies.
To recover lost senses, that's not a goal of my work. And there's a lot of evidence already that indicates that's really challenging, because the plasticity of the brain, when you don't use a resource, the brain trains it to do something different. So, for example, there was a company called Second Sight. I mean, I shouldn't be citing companies here, but that came out with a retinal implant technology that was able to stimulate the retina and bring vision back to people who had never been able to see. And I think it universally didn't work, because the people's brains had already taken those resources and applied them to other things. And it would almost appear you would present an image to someone, and to them I'm exaggerating here, but would seem like someone was just screaming in their head, and because it was like you're stimulating nerves that have been linked to do other things. So the idea of replacing a missing sense is really not on my pathway, but bringing that awareness that might have been there in through a new pathway. So bringing, let's say for sight, for example, if someone is blind, there may be some visual awareness information that could be then put into a tactile information communication pathway that would allow you to get visual information without directly thinking of it as being the substitution for sight.
So it could be like a cane for people who is blind, who was born blind.
Well, right. So what we could do, for example, is create a sensing modality that will tell you if something's approaching you, or whether it's light outside, or even we could even imagine that we could mount some sensor on my finger that would tell me how hot or cold something is, or what the color is, right? And then that information could be presented. Now, I'm not sure if a person who's blind really cares about color, so deciding what information is going to be the most valuable. But any type sensing, I'm not presenting the image to them, but we're presenting sets of information that could allow them to navigate life more effectively through a different sensory channel. Like in this case, tactile. Tactile seems to be the only open. I mean, the idea of creating sense as though our nose can detect it, and probably not, and taste things, and those are slow pathways. Tactile is really, really interesting because it's got more bandwidth than our eyes do. So I would really be interested to see if in the future we're all wearing these tactile suits, and that we train our brain to take in, massive data in parallel, and train a new part of our brain to manage attention for tactile inputs. Like right now, I mean, I can look around this room and there's a lot of data, and I have to choose what to put my attention on. If I want to know the time, there's a clock, but I only choose to pay attention to it. Ultimately, the same thing can be done in tactile inputs, where I could be getting tactile inputs all over my body always, and I just choose when to pay attention to certain things and say, oh yeah, if I want to know the time, I pay attention to this input, and then I know the time. If I want to know the color of my fingertip sensor, I pay attention to that signal. And that's That's yet to be seen whether the brain can actually do that, but our goal is to create the technology that will enable that exploration in the future.
Thank you. One last question.
I'm not sure I understand this one. Electronics networks can support the amount of data. The human data levels are generally quite slow. So if you think of things like a heart rate, if I want to know someone's heart rate, then that's data that only needs to be updated on the order of hertz. So the input data streams need to be higher bandwidth in order to extract these higher level features. But most of the things humans interact with are very slow compared to things that computers interact with. So we can take in a lot of data and process that, and then we have very limited amount of data that we would need to present to the human. Of course, that's within a certain window. As I just said, my goal would be ultimately to bring in a really extensive amount of parameters and present that to the human so that their attention could choose which they want to listen to and which they don't. But I don't see this. The idea that we're proposing is that this all would be done sort of in individual wearable devices. So you think of a smartwatch, with significantly more capability. How that would involve in passing things through networks. Yeah, I mean, there's a lot of open questions. As we create new technologies, their implications with other existing technologies becomes new things that we have to ask. Certainly in the whole concept of 5G communications is revolved around the fact that there's so much more data being thrown out on the internet now. So if what I'm proposing to do is to put sensors on everybody, we have to make some decision about whether does that all go off to the cloud somewhere, or do we just utilize local information? And I suppose most people probably would not want all of their personally acquired data to be thrown off into the cloud. And my goal is really not to make the cloud smarter, but to make individual humans better able to operate in their local environment. So in my vision, all the data is quite local. So it's just the sensors I collect. Maybe I'm interacting with Martin. Martin and our systems share some information so that we can be smarter about each other. So yes, but potentially some limits that have to be looked into.
Thank you for your answer. Is there any other question? It's the moment. In this case, thank you everyone for attending this talk, and thank you, Professor, for presenting this talk. Thank you.
Yeah, thank you, Martin, for organizing it, and thanks everybody for attending, and all the people who may be watching in the future.